When we picture a molecule, we often imagine a rigid structure, discrete atoms locked together like building blocks. But at the atomic scale, a molecule is a highly dynamic quantum system. It is a vibrating cluster of positively charged nuclei, surrounded by a constantly shifting blur of probability representing the electrons. Every single particle in this system exerts a pull or a push on every other particle. The electrons repel each other, the nuclei repel each other, and opposite charges attract each other. All of this happens simultaneously, in continuous motion. To describe the total energy of this system, quantum mechanics uses a mathematical framework called the molecular Hamiltonian. This equation must account for every variable governing the particles. The first two terms represent the kinetic energy, the physical motion of the electrons and the nuclei. Those are relatively straightforward. The problem lies in the interactions. The final three terms represent the electromagnetic attraction and repulsion between all these moving bodies. Because the particles are constantly moving, the repulsion between any two electrons depends on exactly where both electrons are at that exact microsecond, but their positions are dictated by the repulsive forces they exert on each other. This is known as the many-body problem. Because every particle's position relies on every other particle's position, the full Schrödinger equation for even a simple molecule cannot be solved exactly. If the governing equation of molecular chemistry is mathematically unsolvable, we face a strict barrier. Without a solution, we cannot accurately predict how a new drug will bind to a protein, or how an organic material will emit light in an OLED display. To bypass this mathematical wall, physicists in the early 20th century realized they had to substitute pure calculation with physical logic. One of those physicists was Robert Oppenheimer. Working alongside his mentor, Max Born, they formulated a workaround that would strip away the most paralyzing variables of the Hamiltonian equation. The mathematical compromises they and others established form the core approximations of modern computational chemistry. They are the tools that allow us to calculate the unseen. The first workaround is the Born-Oppenheimer approximation. It relies on a specific physical property of the particles themselves, their mass. A proton is roughly 1,836 times heavier than an electron. Even the lightest nucleus has massive inertia compared to the electrons orbiting it. Because of this extreme mass disparity, nuclei move sluggishly. From the reference frame of a fast-moving electron, the slowly drifting nuclei appear practically stationary. Born and Oppenheimer used this perceptual quirk to split the unsolvable math into two solvable halves. First, we temporarily lock the nuclear coordinates in place. By treating the nuclei as fixed points, we can solve the complex equation of electron motion on its own. We visualize this relationship using a chart plotting internuclear distance against total electronic energy. Once the electron energy is calculated for one fixed position, we move the nuclei slightly, lock them, and recalculate. This creates a curved valley called a potential energy surface. As the nuclei are brought closer together, the sharing of electrons lowers the total energy. If they get too close, physical repulsion sharply spikes the energy back up. The exact minimum point of this curve reveals the most stable arrangement. This minimum point gives us the equilibrium bond length. The Born-Oppenheimer approximation allows us to calculate molecular geometry precisely because it treats the fast electrons as an energy landscape that guides the slow nuclei. With the nuclei positioned, we have to determine exactly how the electrons hold them together. To see this, we look at the simplest possible molecule, the hydrogen molecular ion, consisting of two protons and a single electron. Two positively charged protons naturally repel one another. The structural integrity depends entirely on that single negatively charged electron fighting against the outward push. At this scale, the electron does not sit like a physical glue between the protons. The chemical bond is entirely a quantum wave phenomenon. We determine the shape of the molecule by combining the atomic orbital waves of the two individual protons. When the wave functions add together, they create constructive interference. The electron density concentrates directly between the two protons, pulling them inward. We call this a bonding molecular orbital. Alternatively, wave functions can subtract, causing destructive interference. This creates a node of zero electron density between the protons. With nothing to mask their repulsion, the protons push apart. This is an antibonding orbital. A bonding orbital lowers the total energy and stabilizes the structure. An antibonding orbital raises the total energy and destabilizes it. The hydrogen molecular ion proves that a chemical bond exists specifically because an electron spreads its wave function over multiple nuclei, achieving a lower energy state than it could on its own. The hydrogen molecular ion has one electron. Ordinary hydrogen gas has two. Now, electron-electron repulsion returns to the equation, bringing the many-body problem right back. To solve for many electron systems, chemists rely on a third workaround, the Hartree-Fock method. Instead of calculating the exact repulsion between every individual electron pair, Hartree-Fock treats each electron as if it is moving through a single average field of negative charge generated by all the other electrons combined. This simplifies the math, but the field itself depends on the orbitals of the electrons, and the orbitals depend on the field. To resolve this, the system uses a self-consistent field procedure. We guess the initial orbitals, calculate the resulting average field, and use that field to generate better, more accurate orbitals. The algorithm repeats this loop over and over. Guess the orbitals, calculate the field, improve the orbitals. The cycle continues until the orbital shapes and total energy stop changing. Once the math settles into consistency, we have our answer. The Hartree-Fock method gives us a practical, scalable mechanism to estimate the structural energy of highly complex molecules. By combining these approximations, we map reality. The Born-Oppenheimer approximation provides the physical geometry, while wave interference and Hartree-Fock mapping reveal the discrete energy levels of the molecular orbitals. The properties of a material are dictated by its frontier orbitals, specifically the highest occupied molecular orbital, or HOMO, and the lowest unoccupied molecular orbital, the LUMO. Looking at this energy level diagram, we see the gap between these two boundaries. When a photon of light strikes the molecule, it provides the exact amount of energy needed for an electron to leap from the occupied HOMO to the vacant LUMO. The physical distance of that energy gap controls the exact wavelength of light the molecule absorbs or emits. It determines the specific color of an organic dye, the absorption capacity of a solar cell, and the visual output of an OLED screen. The macroscopic characteristics we observe in chemical materials are direct translations of these microscopic quantum energy states. When millions of atoms bind together to form a solid structure, these individual molecular orbitals overlap and blur together, forming continuous energy bands. The exact same wave interference principles that hold a single electron between two protons in the hydrogen molecular ion simply scale up. They become the band theory of solids, controlling how charge flows through the semiconductors in our computers. By separating the math into solvable approximations, we bypass an intractable equation. We translate the abstract wave-like behavior of electrons into the engineering foundation of modern material science.